Alright, so in this lesson we're going to discuss write concerns and how they can provide a different level of write durability in our application. If you're not sure right now what write durability is, no worries, we'll cover it in this lesson. So for right now, let's just consider a small supermarket application using a replica set as its data source. Whenever a customer puts an item into their cart, the application will send a write statement over to MongoDB, and that write will be received by the primary node of the replica set. So the first thing the primary node is going to do when it receives this write is it's going to apply the write and its copy of the data. And by default, as soon as it's done performing the write in its database, it's going to send an acknowledgement back to the client. So at this point, the client has received a write acknowledgement back from the database, and it considers the write to be complete. It assumes that the secondary nodes will replicate the data sometime soon, but it doesn't actually have any immediate proof of it from this acknowledgement alone. So that was an example of a write with write concern W1. The number 1 here refers to the number of nodes in the set that must apply the write before a client gets an acknowledgement back from the driver. In this case, it was just one node. This is the default behavior in MongoDB, so if you send a write to MongoDB without a write concern specified, it will use W1 by default. So now let's consider a different level of write concern. Our shopping cart application sends a write statement to the primary node, and the primary applies that write just like it did before. But this time, the primary waits before sending an acknowledgement back to the client. And what is it waiting for? Well, before sending an acknowledgement of the write back to the client, the primary will actually wait for one of the secondary nodes to replicate the data. When the secondary applies the write, it will send an acknowledgement back to the primary saying, hey, I applied this write to my copy of the data. Once the primary knows that in addition to it having applied the write itself, one of the secondaries has also applied the write, only then will it send an acknowledgement back to the client. This write was sent with W majority, which means that the client isn't going to get an acknowledgement back from the driver until a majority of nodes in the set have applied the write. In this case, it's a 3-node set, so we only needed 2 of the nodes to apply the write. You can think of W majority as a kind of contract with the client, that this write will not be lost even in the event of host going down. If an application sends a write with W majority and gets an acknowledgement back for that write, it knows that even if the current primary were to go down, one of the secondaries in the set has also captured the write. So with W majority, the connection is going to wait for a majority of nodes to apply the write before sending an acknowledgement back to the client. For that reason, it takes a little longer and is subject to replication lag. But there's no additional load on the server, so the primary can still perform the same number of writes per second. However, W majority essentially guarantees to the client that a write will not be rolled back during failover, because the write was committed to a majority of nodes. This is useful when some of our writes are vital to the success of the application. A common example of this is a new user on a website. These types of operations must succeed because without an account, the user can't really do anything else on the site. So I just want to discuss one more write concern, W0. By now you must have realized that when the value of W is a number, it's the number of nodes that must apply a write before the client receives an acknowledgement. We can pass any number here to the W field, but it will throw us an error if this number is higher than the total number of nodes in the set. Following that rule, when W is 0, none of the nodes in the set actually need to apply a write before the client gets acknowledgement. This means that when we're using W0, there's a chance that we get acknowledgement before any data has actually been written. So if the server crashes, we might lose a few writes. This type of write is referred to as a fire and forget operation because it sends the write and doesn't really worry about the response. But this isn't entirely true because the acknowledgement from a W0 operation can also alert us to network errors and socket exceptions. So the client can implement some logic to figure out if the write was actually received by the database. In any case, writing with W0 is very fast and can be useful for less important writes that occur frequently. For example, if an Internet of Things device is sending a ping to Mongo every 2 minutes to report its status, it might be okay to speed up every write operation at the risk of losing a few writes. So to recap, W1 is the default write concern in Mongo, and it commits a write to one node before sending an acknowledgement back to the client. W majority will make sure the write was applied by a majority of the set before sending an acknowledgement back to the client. This means the application will have to wait a little longer for a response, but it should not have a performance impact so long as you have enough connections to the primary to handle your requests. W0 does not commit the write at all, but sends an acknowledgement back to the client immediately. So there's a slightly higher chance that we lose data in the event of a primary going down.